My name is Gabriela Cornejo, and this is my video lab report for Lab 5 on Faraday's Law. The purpose of this lab was to collect observational data of a falling magnet through a conductive tube. We did this by dropping a bar magnet through a tube of aluminum foil. So by collecting the data ourselves, it provides us with a better visual frame of reference and understanding of the information we've learned in lecture. The other purpose was to model the magnet and tube's interaction computationally, and the computational model is what allows us to fully see what is going on inside the tube and why the interactions occur. The results ended up being that the magnet took 1.232 seconds to fall through the tube in real life and only 2.269 seconds in the simulation. Some of the fundamental physics principles used in this lab include Faraday's law for calculating the change in magnetic flux during the experiment to find the current in each of the rings throughout the tube, the Biot-Savart law for calculating the force exerted on each current-carrying ring by the falling magnet, Newton's third to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings, and Newton's second law to find the position and velocity updating code to model the motion of the falling magnet. To start the experiment, we first dropped a single bar magnet down a tube of aluminum foil 5 times. We measured the time it took to fall through and found an average time of 1.232 seconds. We used aluminum foil rather than a ferrous tube because it's not magnetic, thus the magnet can fall completely through the tube with no issue. Shown here are some of the measurements from the experiment, including the dimensions of the tube, the magnitude of the magnetic dipole moment mu from Lab 3, and the mass of the magnet. The biggest takeaway was that when the magnet fell through the tube, it fell slower than it would have in free fall. The next part of the lab was to create the computational model. So to start that off, I just inputted the physical constants and the dimensions of the aluminum tube along with initializing the graph. This next part is the code that actually creates the tube itself along with the falling magnet, and it just sets up some of the numerical parameters for the simulation itself. This part of the code finishes creating the visualization for the bar magnet with the magnitude of the magnetic dipole moment mu being 1.83. It also sets some more initial conditions and is where I define the magnetic field function and the function for finding the change in flux over time, which will both come in handy later. This part of the code is the while loop that actually simulates the magnet falling through the tube, and it includes the calculation for the force of gravity, the computation for d flux over dt, and the computation for finding the current in the rings. This last part of the code first determines the color of the current in the simulation that you'll see in the next slide, and it also finds the magnetic field in all the rings so that we can find the magnetic force on the magnet itself. It then finds the total net force on the magnet using the gravitational force and the magnetic force, and then it updates the velocity of the bar magnet and its position and plots them on the velocity versus time graph that you'll see next. So this is what my computational model ended up generating. So to the left is a screenshot of the magnet before it falls through the tube, and then beneath that is of the magnet as it's falling through the tube, and that blue ring around it is showing the direction of the induced current. The graph to the right shows how the velocity of the magnet changes over time as it's falling through the tube. The way it was supposed to work out is the magnet was supposed to reach a terminal velocity and kind of stay constant in the tube, but I think because my value for the magnetic dipole moment was so small, it doesn't really plateau off like it's supposed to, so my magnet ends up only staying in the tube for 0.269 seconds, and this is the resulting graph. So like I mentioned earlier, the color of the ring on the tube is supposed to show the direction of the induced current. So as the magnet fell through the tube, you could see that my simulation had blue rings on it. And so since the magnet is falling downwards, the increasing change in flux is downwards, which means the induced current is going to be flowing counterclockwise opposite to the change in flux. So that means that the blue rings demonstrate counterclockwise current, and if there were any red rings, they would be clockwise current. The total time in tube in the real world was much greater than that of the simulation, and it's most likely due to my calculated value of the magnetic dipole moment, mu, from Lab 3, because when I tried different mu values, the higher they got, the closer it was to the real life value. So if I wanted my simulation to be more accurate, I would use a different mu value, or use more rings and analyze the magnet at more points throughout the tube. If the resistivity of the conductor were reduced as close as possible to zero, then by Ohm's law, the induced currents would be larger. This means the magnet would fall slower through the tube. If we were to cut holes or slots into the tube, then the magnet would fall faster. This is because the magnetic force from the rings would decrease and there would be less induced magnetic fields. In conclusion, the real-life simulation found the time in the tube for the magnet to be 1.232 seconds, and the computer simulation found it to only be 0.269 seconds, which is significantly smaller, most likely due to the varying value of the magnet's magnetic dipole moment, mu.